So a very good morning to Dr. Arif and Prof. Shang. So we are from Group 9, so we are going to present our well completion project for today. And the member included in Group 9 is Cheng Mei Xuan, and second one is Tae Yuan Jun, third one is Adam Haziq, and the fourth one is Muhammad Haziq Afandi. So for our presentation for today, we will cover total 8 outlines for today, which is introduction, casing design, cementing program, perforation, completion string design, downhole tool selection, risk mitigation, and conclusion. The first part we will cover is the introduction of this project. So this part will include all the well properties and formation properties. So typically, our wells is an injection well, and the lithology is mainly carbonate formation. The net pay thickness is about 70% meter, and the borehole temperature is about 91 Celsius. So there's two gas content inside, which is CO2 and H2S. CO2 we got content of 3.2% and H2S we got 17% ppm. So this is definitely evaluated as a corrosive environment. As the sanding risk is very low, so we are suggested to use open hole or case holes is both accepted. And the well trajectory is totally vertical, so no need to calculate as a horizontal well. So the well completion is mainly followed by step by step. So the first step is typically our casing design. So on the first step of casing design, intermediate design become the first thing that we need to decide it have or have not. So our well TVD, which is total vertical depth, is 7,920 feet, and our formation pressure is about 11.42 ppg, and our surge swept factor is 0.3 ppg, safety margin is 0.2 ppg, and our sticking pressure is 2,200 psi. So the first thing we need to do, we need to add all the formation pressure, and of the factor and the margins inside, we will get 12.22 ppg. And from the 12.22 ppg, we will refer to the graph. So the graph shows that it didn't intercept with the formation pressure, so there's no intermediate casing required. After that, we need to decide is there any differential sticking occur or not. So we will need to use our formation pressure minus by our mud weight, then followed by the equation, we will get our pressure, which is 867 psi, which means there's no differential sticking occur and there's no liner required in this casing. So after we decide of the intermediate casing, now we will proceed to our surface casing. So surface casing is compulsory for every well. So for the surface casing, we will calculate it using our EWM kick formula, which is as shown in the slide. And within the formula, and we'll compare it with our Eaton charge. And also we can get the surface casing depth, and it shows that it's between 2,000 and 3,000. With that, we can use our interpolation method, then we can get our surface casing height, which is about 2,612 feet. So after we have calculated the intermediate casing and the surface casing, so finally we can decide our casing design. So this is the final casing design we are going to use. So first of all, we will have our conductor. The total height is at 500 feet, and our diameter is 30 inch, the inner diameter is 28 inch. And also we will add a bit size, which is 36 inch, and this means the whole size will be the 36 inch also. And after that, we will have followed by our surface casing, which is at the height of 2,612 feet, and the outer diameter is 20 inch, and the inner diameter is 18.73 inch. Then for the surface casing, we decided to use a grade of L80 and a nominal weight of 133 pounds per feet, because our environment is corrosive as is included H2S inside. So, and we are using 26 bit size for our surface casing. After that, we will follow by our production casing, since we do not have any intermediate casing. And the bit size we are going to use is 12.25 inch. And for our production casing, we're also using the same grade, which is L80 for the production casing, but the nominal weight is about 53.5 pounds per feet. The outer diameter of the production casing is 9.625, and the inner diameter is 8.535 inch. After that, we will be followed by the last part of our well, which is red hole, which has 30 feet. After that, we also have a steel track of 2 range of R3, which is about 84 feet. And for this well, we assume that our open hole access is 30% and our top of cement is 656 feet above previous casing shoes. For our slurry density, we decide to use a 10 ppg, which is between the formation pressure and the fracture gradient, and the pump is about 25 cubic feet per minute. And this is for our casing design.
Assalamualaikum warahmatullahi wabarakatuh. My name is Adam Haziq. Next, we're going to go on cementing design. So before that, before we go to the calculation and all, let me give you a quick background on why cementing matters. So cementing is a process where we place a cement slurry in the annular space between the casing and the wellbore itself. So the purpose of doing cementing is to zone is because of zone isolation, which it can prevent fluid uh, migration between formation. Next is structural support for the casing, and lastly is the correction protection. So right now we're gonna cover three casing string. So the first one is conductor, the second one is surface, and the third one is production casing. So each cemented at a different depth with different requirements. So the conductor, of course, the shallowest next, followed by the surface casing, and the last one is production casing, which is the deepest. So for each string, casing string, we calculate same four things. For the first one is slurry volume, second one is a sack of cement, third one is water volume, and the fourth one is the pumping time. Now let's go to the calculation part. Next, let's go to the cementing formula. So we use four formula for the first one is slurry volume, second slurry yield, third is sack, and four is the pumping time. So the first one, we calculate slurry volume. Basically, it's just the annular space between the hole and casing, multiply it by depth, and then we plus with 30% excess. So the next one is slurry yield. So this how much volume can one sack of cement produces. So then we divide it with total volume by yield to get the number of sack, and then lastly we calculate the pumping time by dividing the total volume by pump rate to get pumping time. So let's move on to our cementing design. So next is our result. This after the calculation, this is what we get. So the first parameter is slurry volume, which the conductor casing we get 14.03, I mean sorry 1403.87, and as for the surface casing we get 54.26.11. Then the production casing we get 3145.39. That's for the slurry volume. And then as for the sack, the conductor casing need around 274 sack. Surface casing need around 1058 sacks. And production casing needs around 614 sacks. So for the water needed, so conductor casing need around 148.99 BBL. The surface casing needs 575.29 BBL, and the production casing needs around 508.74 BBL. So next, lastly the pump time. So it took about 2 hours and 36 minutes for pumping conductor casing, 6 hours and 80 minutes to pump surface casing, and the lastly production casing took about 4.17 hours. So to wrap up everything, here what we can take from the cementing design. So across all three casing string, the surface casing requires the most cement, which is 1058 sacks and nearly 7 hours of pumping. So this is expected given the larger annular space and longer cement column. So as for the production casing, well, even though it is the deepest, but it requires a few sack than the surface casing because of the production casing smaller casing diameter. So in this proper planning of site water volume and pump time can ensure the cement is placed before it sets. So which is critical for the well. So that's all mm, from me, casing design.
Now, I will continue with completion string design selected for our well. So for this well, we selected a case hole water injection completion. This is because the main objective of the well is to inject water into the carbonate reservoir to provide pressure support and improve the sweep efficiency. So even though the standing risk is low and open hole completion is also acceptable, but K-hole completion is more suitable because our wells is already include our production casing, our cementing and perforation strategy. So the selected target injection valve is approximately like 2,323 meters to 2,403 meters. So this interval was chosen based on the simulated valve log where the reservoir quality is better, the gamma ray value is lower, then the resistivity and porosity show improvement compared with the upper sections of the log intervention. So since this is a vertical valve and the reservoir is one of the main carbonate interval, so a single zone injection completion is selected. Besides of that, we continue with tubing. So for tubing, we propose a 3.5 inch of injection tubing string. This tubing string size is suitable because the valve is vertical and the valve depth is moderate. So the tubing provided a dedicated path for water injection from the surface to the reservoir. So it is also help protect the production casing from continue our injection pressures and corrosive fluids. Apart from that, we continue with material selection. The tubing should be like L80 grade, internal coated or corrosion resistant alloy. This is because the valve contains CO2, carbon dioxide and H2S, which will create a corrosion risk when mixed with water. So a hydraulic set retrievable packers is proposed as around 2,315 to 2,320 meters, which above the injection interval. So its function is to isolate the tubing casing annulus, ensure the injection water enter only through the selected perforated interval. So finally, the completion fluid should be clean, filter, solid-free brine. So this selected brine should be minimize formation damage, prevent perforation pluggings, and protect the whole equipment from corrosion. So overall, this completion string design supports safe and efficient water injection while maintaining valve integrity.
Next, I will explain the perforation strategy selected for this water injection well. For this project, we selected a jet perforator, also known as the shape charge perforator, because it provides deep penetration to the casing asymmetry and reservoir formation. This type of perforator is widely used in the petroleum industry due to its efficiency and reliability. Since our well is completed in carbonate reservoir, deep penetration is important to ensure good hydraulic communication between the wellbore and the formation while reducing the effect of near wellbore formation damage. We also selected a retrievable hollow carrier gun. This type of gun absorbs excess explosive energy, which minimizes damage to the casing and cemency. In addition, the gun can be retrieved after the perforating operation, making it safe and more cost-effective. For the perforation design, we selected a shot density of 6 shots per foot with a with a 180-degree phase angle. This configuration provides sufficient flow area for water injection while maintaining the mechanical strength of the casing. We also selected a deep penetration shape charges so that the perforation tunnel extends beyond the damage zone around the wellbore, improving injectivity. A standard perforation diameter is adequate for this water injection application. Because the well is vertical, we choose wireline conveyed perforation or WCP. This method is simple, economical, and provides accurate depth positioning using a casing collar locator or CCL. Another advantage is that the perforating gun can be retrieved after the operation. For the perforation technique, we selected unbalanced perforating. During perforation, the wellbore pressure is maintained slightly lower than the perforation formation pressure. This allows formation fluid to flow immediately after the charges are fired, cleaning debris from the perforation tunnel. As a result, formation damage is minimized and injectivity is improved. To further reduce formation damage, the perforating operation will be carried out using clean filter completion brine instead of drilling mud. This operational sequence begins by replacing the drilling mud with completion brine, followed by running the wireline perforating gun to the target depth. The depth is confirmed using the CCL before establishing the required underbalanced pressure. The shape charges are then fired. The perforating gun is retrieved, and finally an injectivity test is conducted to confirm that the well is ready for the water injection.
Then I will explain with the downhole tool selected for this well. So the first one tool is the safety valve with SSSV. Is installed inside the tubing string for an emergency barrier. So for the water injection valve, the safety valves can help prevent like uncontrolled flow or blackflow from the reservoir to the surface if surface equipment fail. So since the valve contains carbon dioxide and H2S, so the safety valve should also have suitable corrosion resistance and pressure rating. Then the second tool is landing nipple. This because it's installed inside the tubing string at a selected depth, usually above the backer. The function of the landing nipple is to provide a sitting profile for airline through. It allows the future well interventions and pressure monitoring, isolations, and workover operations. So this makes the complex string more flexible for future maintenance. Then we continue with the tools, which is sliding sleeve. The sliding sleeve will allow the communications between the tubing and the annulus when it requires. So it's useful during fluid displacement, valve cooling, circulations, or future workover operations. So this means we can circulate the fluid without pulling the whole completion string. Therefore, the sliding sleeve will improve the operational flexibility and safety. Then we continue with our main tool safety. Hydraulic set retrievable backers. It installed at approximately 2,315 to 2,320 meters, just above the injection interval. The backer can seal the annulus between the tubing and the casing. Then this will force the injector water to flow through the tubing and enter the reservoir only through the selected perforations. Then it also protects the casing annulus from direct injection pressures and corrosive fluids. Then the backer must be rated for the bottom hole temperatures of around 31 degrees Celsius and expected injection pressure. Since this is a water injection valve, the pressures and temperature changes can affect the backer performance. So a retrievable backer is selected because it can be removed during the future workover if there are any injection corrections or mechanical problems. Then the next one, we'll choose the tools, which is tubing seal assembly. It provides a reliable seal between the tubing and the backer, may include the seal units slot like J-slot or straight slot body. Then, and also the centralizer, which can help the lower tubing to reduce the mechanical damage during installation. Then the last tool shown is injection check valve. This valve can prevent the black flow into the tubing when injector stop. I think it's important during the shut-in or pressure changes because it helps maintain the injection controls and protect the surface equipment from unexpected reverse flow. So we continue with the final part. I will explain about the main risks and how they are mitigated. So the first risk is for formation damage. Since the formation is carbonated, permeabilities and can be reduced if solid, scales or debit plugs the pore space. So to reduce this risk, we use clean injection fluid system and apply a scale inhibitor program. So if required, the periodic acid stimulation can also be conducted to restore the injectivity. Then the second risk is pressures and fracture control. During injection, the bottom hole is injection pressure must be kept under the fracture pressure of the formation. If the pressure is too high, unwanted fractures may form, then the water may move into the intended zone. So to avoid this, we conduct a step-rest injection test, monitor pressures in required time, so the maintained injection pressures will be below the fractures limit. In addition, the other risk is corrosive fluid. Since we mentioned that the valve contains the carbon dioxide and H2S, which can cause the tubing corrosions and possibility surface stress cracking. So to reduce this risk, the corrosion-resistant tubing or internally coated tubing should be used. So to continue our corrosion inhibitor injections and oxygen-free injection waters are also recommended to protect the tubing and downhole tools. Then in addition, the valve integrity will failure. So this will include the bacterial leakage, annulus pressure build-up, or proximity isolation. So to mitigate this risk, a hydraulic state retrievable beaker is selected, I just now mentioned, and the beaker should be pressure tested after setting. So the Siemens bond verification should be also carried out before the injection to confirm the good zonal isolation. Then moreover, the annulus pressure should be monitored regularly to detect any early sign of leakage. Overall, these risk mitigation steps are important to ensure safety, controls, and long-term water injection performance.
In conclusion, our proposed completion design is suitable for a vertical inverter injection well in a carbonate reservoir. We selected a case-hole completion to provide better zonal isolation, maintain well integrity, and allow future well intervention. The casing, cementing program, tubing, beaker, and completion fluid were carefully selected to ensure safe and efficient water injection while minimizing corrosion and formation damage. For the perforation strategy, we selected wire-line conveyor perforation using jet perforator with 6 shot per foot, 180 pacing, and under balance perforating to maximize injectivity and improve communication between the wellbore and the reservoir. We also incorporated suitable downhole tool to enhance well control, operational flexibility, and equipment protection. In addition, we developed a comprehensive risk mitigation plan to manage potential issues such as corrosion, formation damage, beaker leakage, scale formation, and injectivity decline. Overall, the proposed completion design provides a safe, reliable, and cost-effective solution that supports long-term reservoir pressure maintenance and efficient water injection. Thank you.